I have a PhD in electrical engineering from University of Illinois. I started my first sort of 20 years in academia as a professor at University of Illinois and at Northwestern. And then came to the corporate world about 12 years ago, ran HP labs worldwide for about 5 years. And I started working on sort of IoT and digital twins while at HP Labs. And then I had the chance to be CTO at two large industrial companies, ABB and Schneider Electric. And as Hans was saying, right, GE spent a lot of time and energy on building their Predix platform and so on. So ABB asked me to kind of take a look at a similar thing as Predix. I helped them build their Ability platform. And I went to Schneider, helped them build their EcoStructure platform. And the reason these people were building these platforms was they had a lot of assets. ABB had transformers, they had switchgear, they had robots, and those robots and transformers were in the field. And there is a services business they wanted to sort of accelerate and make it more profitable. And so by connecting all those assets to an IoT platform, they could do remote services of these assets, and when these things fail, they would immediately know when these assets were failing, and then they could do predictive analytics and say, okay, this is when it's about to fail, and I'm going to fix it before it fails. This is sort of why the large industrial companies are interested in digital twins and so on. So I was building digital twins at ABB and Schneider Electric. And I was a customer of ANSYS, and it occurred to me that unless you tie sort of what is called data analytics-based twins with physics-based twins, that's how I got into this area of digital twins. And so what I'm going to talk to you about is my personal journey, what I have learned, and sort of the challenges and opportunities of digital twins, and again in various industries. Okay, let me keep going. Otherwise, we will.
Yeah.
The interesting stuff will be at the end, so it should be okay.
Yeah.
Okay. So hopefully you can see my screen.
Yes.
Okay, perfect. So what I was essentially saying is that this is what I'm going to talk about. Provide an overview of digital twins, and then essentially the rest of the world uses data analytics-based twins. ANSYS was building physics-based twins, and now the new aha moment that we have figured out is how you can do hybrid digital twins by combining physics and data analytics. And we'll show some results with some actual customer use cases. So, so let me first define what a digital twin is. Now, there's a digital twin consortium that has recently been formed, and ANSYS and Microsoft and Dell and a few other GE, they're all members of the consortium. And this is the definition that they have come up with, which is a digital twin is a virtual representation of real-world entities and processes. So think of a jet engine. You have a real-world jet engine, and you have a virtual representation of a jet engine. So people oftentimes confuse digital twins with just a simulation model. The next part is what makes it a digital twin. So if you have a model of the asset, that's not a twin. That's just a model. What makes it a twin is this virtual representation is actually synchronized with the real asset through an IoT platform, right? So the actual jet engine is doing something. You're collecting data, you're measuring the pressure, temperature, velocity, noise, whatever, and you're carrying that information. There's a two-way information flow from the real asset to the digital asset, and then information flowing back to the other side, right? And it is synchronized at a specified frequency. You can synchronize it every hour, every second, every minute, every microsecond. And you can synchronize it at specific fidelity, right? Whether I'm trying to be 10% accurate or 5% accurate and so on. That's what makes a digital twin. So this is a very short definition, but it actually gets to the key idea of a digital twin. And essentially the value is you track the past behavior of the asset, you provide insights on the present, and most importantly, it provides sort of predictions into the future. That is why it is so important. And it turns out that digital twins have been used to increase revenue, to reduce costs, and to gain competitive edge. So digital twins have been used in different phases of product design. So when you are designing a product, you have an ideal product like a jet engine you are making, and you have an ideal product, you have CAD tools and so on. and that's the design thread of the digital twin. It's the ideal structure, ideal materials, and so on. Then that jet engine actually gets manufactured by GE. Then they make 100 of these engines, and each of the engine is slightly different from the original ideal design, right? This is a perfect triangle on a CAD. When you manufacture it, that triangle edges became a slightly sort of messed up and so on. And so that's kind of what is in the manufacturing digital twin. And then you have the operate version of the digital twin. After 20 years, that same jet engine goes into and has different, it evolves. You have fatigue in the jet engine and so on, and you can still sort of try to create a digital twin of that engine in operations. So there are different phases of digital twin. Digital twins have been used in various industries. In aerospace, this is where things got started. So GE, Rolls-Royce, all these engine companies make digital twins of engines, and they use it to drive sort of better predictive analytics of how frequently, when that engine should be serviced and replaced and so on. They've used it in automotives, used it in manufacturing, in the manufacturing floor. All the assets that you have, the injection molding machines and lathes, if you have to keep them all up all the time, ties to what is called the operational equipment efficiency, OE. People use digital twins for that. People use digital twins in buildings and infrastructure. You can have a model of the building and essentially control the air conditioning, the heating, and the elevators, everything in a building. Similarly, in digital, sort of in oil and gas, people have built digital twins of entire oil wells. So the market for digital twin, it's kind of growing, and which is why companies like ABB and Schneider and everybody is investing so much money in digital twins, right? It is about 3-4 billion today, but it's supposed to grow to about $26 billion by 2025. And depending on the different phases, as I kind of talked about, the design phase, the operations phase, and so on, this is showing the market by those phases. Then if you look at by verticals, right, I kind of talked about aerospace, defense, and buildings and manufacturing. You can see pretty much, I mean, looking at different areas, right, say automotive transportation, it is about 15% today, but it will grow to 25% by the year 2025. So most of the verticals are interested in digital twins. Now, ANSYS as a company, we have about 45,000 customers, and we actually sell our simulation software in all verticals. We are strongest in aerospace and defense. People use it to build airplanes. We are very strong in automotive. People use it to build cars. We are strong in manufacturing. In all manufacturing plants, we are strong in high tech. People use it for designing electronic chips, like the Apples and the Googles of the world. And we are strong in sort of oil and gas, in whatever, right? So in all the areas that you see here, simulation is actually used to do product innovation. So now the question is, what's the role of digital twins and how can we actually build it, right? So the role of physics in digital twins, that's the first thing I'm going to cover. So it turns out that when way back in, say, 10, 15 years ago, when GE built digital twins and with the Predix platform, or when ABB did the digital twins with Ability and Schneider did their thing, they were all building it using data analytics approaches. So you take an asset like a transformer or a switchgear, you attach some sensor to the asset, connect it to an IoT platform like Predix or Ability, collect the data under normal conditions, and you build a little AI system, this neural network, which I'm depicting here. Look at the inputs, watch the outputs. Look at another set of inputs, look at the outputs. And basically, you look at the input and the output, and you start with some random weights in this neural network, and then you say, let me program the net in a feed forward, let me set it to these weights, see what the output is. Well, my output is not quite correct, there's an error, so I do a feed for backward, and I update those weights. I do it again, update the weights. A couple of times we do it. That's how these deep neural networks get programmed. Basically, after maybe 1 million inputs, this neural network knows what it is supposed to do, right? So the advantage is, don't need to know the physics of the assets. It can be a transformer, a robot, or whatever. It always works. It's a general approach. The trouble is, it requires a lot of training data. And these neural networks are only as good as the failure modes that you have programmed it to be, right? So when the Space Shuttle Challenger exploded, right? The number of times the Space Shuttle Challenger exploded, only one, right? So no amount of neural network training can predict the Space Shuttle Challenger exploding. When a nuclear power plant explodes in 3 Mile Island, that happens only once every 30 years, thank God. So essentially, neural networks are good for frequent events. For infrequent events, you actually cannot do it, right? So therefore, you need to rely on physics-based twins. And that's where sort of ANSYS comes in, right? So now let's imagine you're trying to model a digital twin of a bridge, and you're trying to predict the bridge failure. And so you observe a crack on a bridge that happened today, right? December 10th, it's 12 inches long. And through simulation, through ANSYS simulation or Dassault or Siemens simulation, you can say, hey, with all this, the number of cars that are going on the road, so much stress happening, tensile strength of steel is this, and so on and so forth, the crack will grow to 18 inches. We can predict it through simulation. Now, actually measure the crack next week to be 16 inches. In that case, you update the simulation model to slow it down, slow down the crack propagation. Or if the crack is 20 inches, you speed it up. This is what I was talking about, the definition of digital twin, which is a synchronization. We have now synchronized every week with the fidelity that I'm trying to measure it to within 12 inches, right? This is what makes it a digital twin. And if the model is now the model can be a data analytics model, or the model can be a simulation model. It doesn't matter. That's what is at the core of digital twins. So now, using the physics-based digital twins, we have been able to do sort of these things called virtual sensors, right? So suppose you have a pump and you have cavitation that is happening in the pump, means there's some funky behavior happening in the pump. You can put in a sensor inside the pump to say, hey, is my pump cavitating? Well, it turns out if you put a sensor inside the pump will stop acting as a pump. So therefore, you cannot put a sensor in every location in this thing, right? Suppose you have a 5G antenna. Oh, I want to measure the EMAG fields on the antenna. If you do anything to the antenna, it will stop acting as an antenna. So you actually cannot put sensors in everything. Therefore, you can do this through virtual sensors with physics. You can do all kinds of what-if scenarios, like before applying a solution. So you may have, like in autonomous driving, we have done this, right? You're driving a car on Golden Gate Bridge at 9 a.m. in the morning while it's sunny. Now you want to do a what-if scenario. What if it is 9 p.m. and it is snowing in San Francisco? Well, that is never going to happen, but you still want to do this what if. These are things that you can do through simulation based with digital twins. So essentially what we have done at ANSYS in the last sort of 2-3 years is build this physics-based digital twin, which is you have this thing called the build phase, where we build digital twin models using reduced order model ROM technologies. Then we validate the twin, that is actually, this is the model of the bridge with the cracks and so on, and then we deploy the twin. So what does that mean when you talk about ROMs, right? So the world around us is governed by laws of physics, right? So if it is fluids, it is Navier-Stokes equations, and you can solve it with all the turbulence flow and so on and so forth. But it takes like 100,000 hours to run a fluid simulation on just one small, simple example, right? Or if it is structures, it's Euler equations, and it takes maybe 1 million hours to run a crash, whatever simulation. Or if it is electromagnetics, you can use Maxwell's equations. So you actually cannot create these really, really complicated things at the level of the partial differential equations, which is where ANSYS works. So in order to simplify, you build these things called reduced order models or ROMs, and essentially it's like curve fitting, right? You do you run the full simulation with all the accuracy, take at different points, and you try to do a curve fitting in between the points, and that's how you create these things called linear ROMs, non-linear ROMs. And non-linear, if it is a steady state behavior, it's called a static non-linear ROM. If it is non-linear dynamic, you're trying to go after the transient behavior, you can build it. So within Digital Twin Builder, we have all these different technologies to build digital twins. Then once you build that twin, it is like a simulation model. So what you do is then you connect it to an IoT platform. You have an asset like this, whatever, this compressor or engine that you have, and you have a model of the asset, and this model of asset is a software, it's a binary, right? And you connect it to an IoT platform, and essentially you deploy this model to run as a software binary using Docker containers on the cloud or on the edge device. Then, so this is how we have been doing our twin builder. So now, what I want to share with you, and this is the exciting part, right? Where the pure physics-based has challenges, pure database has challenges, and what we have now come up with is this hybrid approach. So just to show this point, right? So as I was saying, a pure database analytics approach, whereas you take your asset, you put some sensors on the asset, and you build a digital twin model, right, using those neural network models. It works, it's general, but it's not always accurate, and it's limited to observed data. The physics-based, simulation-based, which is what I was showing with Twin Builder, right, is accurate, but it takes long, expensive time, right? And there's a problem. So what we came up with is, can we combine the two approaches? And this is a very, very important sort of slide that I want to explain to you. So in the world of digital twins, and Hans kind of explained, hey, everybody's building these IoT platforms and so on, right? So all these assets are owned by these incumbents, right? So when you have an automation company like ABB or Schneider, right? They're the ones that they have the assets like breakers and panels and UPS devices and so on, the robots and so on. In the automotive, the OEMs, the BMW and Mercedes, they are the ones that control the cars, right? Aerospace, the Boeing, Airbus, right, have the airplanes. GE and Rolls-Royce has the engines, right? Energy companies. So all these people actually own the assets. So when I was CTO at Schneider, we used to say, hey, you guys can do whatever with stuff, when our EcoStruxure platform will ultimately be the winner, because when you talk about industrial Internet of Things, we own the things. So whoever owns the things actually controls everything, right? And so essentially all these guys are putting a tremendous amount of energy and effort, right, in building digital twins of their own assets, right? But the approach they are doing is to take a technology of data analytics from companies like Microsoft, like they will take Azure IoT platform, Azure ML, and stick it on this platform, right? So ABB and Siemens and Schneider, they all use the Microsoft Azure platform. So they're using this kind of technology in their stuff, right? Or they will use a C3.ai platform. C3 just IPO today, in case you have not seen it, for $10 billion. So Tom Siebel's company, or Uptake, Spark Cognition. So all these companies are doing data analytics. They are doing a platform by themselves. They don't have the assets, but these companies' technologies are being used by the people who own the assets. And then there are the companies like ANSYS, like ANSYS, Dassault, Siemens, Hexagon, Altair, right? We build simulation models to help these companies on the left-hand side build the robots and the cars and the engines, right? So what we have now figured out is, if you do pure data analytics like this, it's no good. If you do pure simulation, that's no good. We therefore came up with this aha thing. Let's do a hybrid where we combine data analytics from one of these companies into the simulation base and provide value to these guys, right? That is the key message of this presentation. So the way we do this is, first of all, let me show the flow without this white box. So let's imagine that you don't have the white box. This is the rest of the things is just how normal Twin Builder works, right? So I mentioned that when you have these different assets, you can model the world around us, right, through the world of physics, right? So if it is a fluid asset, you are trying to model an airplane wing, where the wing is lifting because of it has that particular shape, right? That can be modeled with our ANSYS fluid dynamics software, which is shown here. Or if you want to model a bridge or a beam and you're applying some force to it, that can be modeled through ANSYS mechanical. Or you want to model a 5G antenna, that can be modeled through HFSS. So at the basic level, we have these detailed solvers that are like as accurate as the physical stuff itself, right? And this is how simulation is typically used in most companies, right? They use it to do simulation-based product innovation. But now that thing by itself, it does not run fast enough to be in synchrony with the real asset. So what you therefore do is do these things that I call the ROM technology, either using linear ROMs or non-linear ROMs, static and dynamic, right? And using this, you build this, you create these software binaries, 10 bits, that will run on a Docker container, on an edge device like an Intel processor, AMD processor, whatever, or on the cloud. That is sort of the normal flow of a Twin Builder. Now, this ROM model, because it runs fast, oftentimes is not that accurate. And so what we have now done is we take this data analytics-based approach. You have asset performance data from sensors. You take that data and you intercept, you have a little model of the compressor or the motor. You take data from these things and you make it accurate. Like it's like I had the model of the crack on the bridge, which is 12 inches long, and I actually saw the crack was 16 inches. Well, I now augment, auto-calibrate, fix the ROM model to make it accurate. So essentially, I'm showing the flow of that bridge example that I showed you earlier. This is our hybrid model. Okay. So I want to make sure that you sort of get how this thing kind of works. So then this is what this is done is now using this digital twin model, right? We can take the physics. We have the CAD model of the compressor or the engine or the jet engine or whatever. And we take sensor data from the jet engine and compressor and engines. And we take engineering knowledge. Okay, you have a pump. Now you can say the pump has these pump curves, right? And you can take these high level descriptions of this asset. Hey, breakers work like this, engines work like this. So you can take the engineering knowledge, the physics simulation, and the sensor data, put it in this blender, which is this model-based decision support. And that is used by digital twins to drive business value, right? These high value applications, such as predictive maintenance. So you have an asset. I'm going to predict that this asset will fail next Thursday. So if you can do it very accurately, well, there'll be no downtime because I'll replace it on Wednesday. I'm in a factory and the factory is not providing the full capacity. I say, hey, my God, it's going at 50% capacity. Why is it? I identify through this digital twin, I find out exactly where is the inefficient operating condition and go and fix it. I can do anomaly detection. I can do diagnosis of the root causes. So there's wonderful things that you can do with this hybrid digital twin technology. This now I want to show, well, does this work, right? So Prith just talked about the theory, does it actually work? Well, yes, it does, right? So I'll just go through some simple use cases and then pause for questions because I really want to keep this interactive. So worked with a company, Phoenix Contact. Again, we have worked with lots and lots of customers. Not all the customers have allowed me to speak. So it's a subset that I will talk about, right? So Phoenix Contacts, they make relays. And the challenge is these relays, if they fail, it can cause tens of thousands of dollars of losses, right? And you could actually, if you could put a sensor inside the relay, you could solve the problem. The trouble is there's no way to, if you put the sensor inside the relay, it will stop acting as a relay. Therefore, you have to use these simulation-based models. So essentially using this hybrid simulation-based model, right, we were able to, the physics-based simulation model, we were able to predict the wear and tear and essentially reduce unplanned downtime. So that's one example, simplest use case. Second use case, much harder, more complicated, is we worked with Volkswagen Motorsports on the electric car. So they were essentially we helped them build electric car that build the world record in all kinds of cars that crossed Pikes Peak in less than 10 minutes, right? This is the world record. Now, last year, we helped them build this car, and essentially through this digital twin, they had one shot at it, right? So they're trying to build electric car, right? That'll go really fast. Well, to make it really go fast, you put a huge motor, right? And it's, oh, you got a high-speed motor that'll give you the torque. Well, if you do a big motor, you need a big battery to drive that motor. Oh my God, if you put a big motor and a big battery, the weight of the system goes up. Oh my God, now it will not go as fast, right? So you essentially, once you build a digital twin model of this electric car, right, you can do these what ifs trade-offs, right? And essentially we partnered with Volkswagen to build this electric car, and they could not even take it on a test drive, right? The first time they went was when they drove this with a driver, right? And they were able to build the world record, right, in this thing. So it's an example of the use of digital twins, right, in a product innovation perspective, right, in the design, where we help them build these linear time invariant ROMs for modeling the thermal behavior of a battery pack. And this is, the next one is an example of an oil refinery. This is the use case is actually Total, the oil and gas company in France. And essentially they do this blending of gasoline and so on. And so it turns out in refineries, it's a very complicated problem, right? You have tens of thousands of pumps and valves and assets and so on. And you're combining this carbon dioxide with this thing, this particular oil, this blending, and at the output comes the 92% ethanol thing that you buy from your gas station, right? And the super unleaded and unleaded and all that kind of gasoline, right? So it turns out when you're doing all these things in a refinery, right, you have all these different assets and all these different blendings and so on. And we were able to, building this simulation-based digital twin, we were able to do the right blending process and essentially help that customer with operational improvements in the range of 10%, saving tens of $billions per refinery. And of course, Total has lots and lots of refineries. So this is showing some details as to how these simulations are actually working and so on and so forth from the actual operating conditions. Next example is that of, so we are working with Rockwell Automation on manufacturing, sort of digital twins of manufacturing. And this is an example of what we did with a consumer packaged good customer who does not want to be named. But of course, the partnership with Rockwell is kind of well known. So it turns out that when you're doing a brand new factory for a customer, right, you have to do commissioning of the factory. The factory will have this many lines, this many assets, there's the injection molding machine, this, and PLCs and drives and automation and so on, all kinds of stuff. So essentially, so Rockwell has this tool software called Emulate 3D, where you can actually do virtual commissioning of manufacturing plants. But that is at a very, very high level. That we combine with the simulation-based digital twin of the different machines that are in the factory. And through that, we are able to do virtual commissioning, right? Once you do the what-if analysis of this manufacturing plant, then you move it into the operations part. And we actually have partnered with this CPG customer on their journey to actually doing the operations part of the manufacturing plant, where we are improving performance and detecting issues like reducing melt making and so on. I hope that from these words you don't understand what the customer is. I really hope so. And then doing sort of analytics and operator training. So essentially, we have been able to do this in partnership with Rockwell, right, for this customer, where we are actually helping them with operations and with operator training. The last example that I will talk about is, again, working with an asset OEM company in the oil and gas area for industrial flow networks, right? Again, as I gave the example of this oil and gas customer, right? In these large settings, you have sort of tens of thousands of valves and pumps and so on. So now we are talking with a pump OEM, right? Here's the company that makes these pumps, right? So essentially, we are taking this manufacturer's asset-centric ability. So in the past, this company could do, I build a digital twin of the asset, the pump, right, or the valve. Now what we are doing is we are doing it for the entire industrial flow network, right? So we have tens of thousands of valves and assets and pumps and so on, right? So in a factory or in an oil refinery, you have this thing called a PNID diagram, right? The sort of instrument diagram, the physical and instrument diagram, right? And it can take that PNID diagram and essentially build a digital twin model of that thing, right? And then based on it, right, we create this physics-based digital twin and we say, oh, here is the pressure and here is the flow, right? So we can say at this point, the pressure will be this and the flow will be this, right? And so through this physics-based approach, combining with this hybrid approach that we're talking about, right, we are able to come up with models, right, which are a pure database model comes in here, and essentially the prior model comes in here, and essentially the new way that we have done is it's super accurate and it gets to the exact value that we're trying to do. So the predicted value of the virtual is now becoming the physical sensor asset in terms of blind test. So literally, we have been able, so if you take a pure database approach, it doesn't work. Pure simulation doesn't work. When you combine it, we are able to do this in a scalable way for industrial flow networks. So last part of my presentation is that digital twin technologies are very, very hard, really complicated, and you cannot build it yourself, right? So it's not ANSYS by itself that can build the whole thing, right? So the ANSYS digital twin ecosystem is partnering with, say, Microsoft, right? So when a company like ABB or Schneider, right, they take their assets, they collect data, they put it on the cloud, right? So we are partnering with Microsoft on their Azure digital twin, right? Working with Sam George's group on the Azure IoT on the edge and Azure on the cloud, right? So this is our cloud and edge partnership with Microsoft. Then we on the different companies use sort of at the application level, they use sort of this the ThingWorks sort of ways of writing these IoT apps So we are partnered with PTC on the ThingWorks IoT app area. Either some of them use PTCs, some of them use SAP's platform. So at the application level, we are partnered with both SAP and PTC from an IoT data analytics perspective. But then we took look at different verticals like manufacturing, and then we are partnering with Rockwell Automation, as I gave you example, right? That Rockwell plus ANSYS, that Emulate 3D partnership kind of works, right? And then we have this digital twin technology, hybrid digital twin that I kind of talked about, is actually a partnership with a startup called Geminus, right? Which is what gives us the industrial flow networks and so on. So it is actually an ecosystem play. People talk about sort of it's a village. It is a village that makes us successful. Now, a village that I want you all to know of is this digital twin consortium. I mentioned this in my first slide where I gave the official definition. This is a consortium. It has now about 180 companies in it. There are five founding members: ANSYS, Dell, GE, Lend-Lease, Microsoft, and actually a couple of other companies have joined as a founding member, like Northrop Grumman, and I think for another company. It's about 150 companies, 80 companies involved. If you want to be a member, if you want to learn more about it, go to digitaltwinconsortium.org. Phenomenal amount of material exists there. The other thing that we are working on is this digital twin definition language in partnership with Microsoft, where essentially, suppose you are trying to build a digital twin of an airplane. Now, an airplane is a system, right? An airplane has a fuselage and has two wings. So click, you create that airplane model out of two wings. You click on the wing, and each wing has two engines. Click. Each wing has two engines. Then you have two engines. Then click on the engine. Each engine has 52 blades. So essentially, you can create this digital twin definition language. It's like in JSON, you're writing it, right? And you create this digital twin model, and that's the how you specify your thing. And then at each level, we use ANSYS to simulate that blade. They simulate the wing flow over the blade. They simulate the engine, simulate the wing, the flow over the wing, they simulate the plane, right? So we can essentially simulate at each of the level in the hierarchy in partnership by leveraging this DTDL. So these are two things that I want this group to know about: the Digital Twin Consortium and the DTTL language. Now, this Digital Twin Consortium has identified different working groups. Again, this group who's in the audience may be interested in what they're doing in terms of technology. So they're creating these reference architectures and taxonomies and definitions that I showed. They have got a digital twin group for infrastructure and buildings, a digital twin group for natural resources and energy, a digital twin group for defense and aerospace and others. So so that's sort of what is going on here. And so that's sort of I managed to finish on time, even though I started late. But basically, I'm super excited about the digital twin industry, right? And it's a $26 billion industry. And there's sort of these two broad areas: the physics-based and the data analytics-based. And people used to think, oh, you should do only database analytics. And then ANSYS and other companies thought, no, you should do physics-based. The new aha thing is you need to combine the two. And the other message is it's an ecosystem, right? You need to be part of the ecosystem, which is being led by companies by organizations like Digital Twin Consortium. Well, thank you so much for your attention. I'm happy to answer any questions you have. Unfortunately, I've not been able to see any of the questions on the chat. So
there's a couple of questions. So I have the first one. Thank you. That was excellent. So I had a question about the Digital Twin Consortium. You guys have obviously put a lot of effort and work into the product you have today. And so my question was, how does what you're doing with the Digital Twin Consortium, does it change it? And what does it look like in the future? Like, how do you see your product changing by being part of the Digital Twin Consortium?
So the Digital Twin Consortium essentially is pushing for standards and interoperability and so on, right? So, I mean, in the past, ANSYS would have done their stuff with a closed ecosystem and so on, and then these things would not work with the PTC's product, the CAD product, or the Microsoft Azure. So the reason you join consortiums is to make sure you have a reference architecture and a way to sort of share information and so on. And if you have like that, the manufacturing working group, right, or the aerospace and defense working group, right? If Northrop Grumman and so on say, hey, I want the tools to work like this, we are highly motivated to be part of this open ecosystem, which is why we joined, right?
Yeah.
And so when you see the founders, you see the different sort of one company per, right? So there is one cloud provider, Microsoft. There's one simulation company, ANSYS. There's one CAD company, Peter.
Yeah.
Essentially, there's a reason. There's one edge, right? It's Dell, not HP, right? So essentially, those people went in there and said, okay, we will try to create the standards, right? So once you have it in the standards, the reference architectures, if that becomes the way the whole world works, everybody, right? So if Dell manages to get to the edge architecture definition, then HP will have to follow, right? If Microsoft creates the thing on the cloud, then AWS will have to follow.
Right.
That's why we went in from a simulation. We wanted to define the stuff from a simulation-based stuff, so that then Dassault and Siemens or whatever sort of will have to follow our thing, right?
Right.
And that's why that's in it. That's what it's in it for us.
So I mean, it at least for your product, it will be a natural evolution. You basically be supporting the use cases today. As the standards evolve, you'll support them.
Precisely.
Yeah. Okay. All right, guys, ask your questions in the chat window. I had a second question. When you were going through the VW example, I think I heard you say that they did all the simulation before they actually built the engine.
Before they built the car, absolutely. The whole thing was built on pure simulation, right? And all the system level trade-offs, right? I will have a motor this size. No, I'll make it twice as big a motor, thrice as big. Oh my God, the weight goes up, right? All of those what if things were done as part of optimization, as part of the design part of digital twin. Then they actually build this whole thing, and in one fell swoop, they had to test it, right? So this is it is showing the power of simulation-based product innovation in action, and that whole thing could have just not gone, but we were able to. So we had a lot of our personal sort of brand associated with it, right? We had that car actually had ANSYS logos all over, and if it did not win, we would have lost, right? But Volkswagen won and we won, so it was kind of a good win for us.
So where did you get the data for the simulation if the car didn't exist?
From Volkswagen. Volkswagen has all kinds of. I mean, they have got. You mean? So this was the simulation data. So and they have simulation data, and they have all kinds of. These car companies have all kinds of sort of wind tunnel data, actual data on different motors and aerodynamics and so on. So they have got tons and tons of data. So essentially, we fuse that experimental data with the simulation data, and that's how we built it.
Okay. Oh, cool. Okay. I mean, I assume they have a lot of data to get started with, right? If you're, okay. Guys, any questions? I have more. I'll carry on asking mine. So one of the things that I've been wondering is who is buying this technology, and I mean, it's obviously some data scientists. We work, or at least in our Meetup group, we're seeing more and more small and mid-sized manufacturers, local manufacturers. Would they be able to deploy this? Like, is this something that's very expensive for them? Like, I mean, or who is your target? Is it the big companies, or do you expect to go down to these small manufacturers as well?
We do. So basically, the reason we have 45,000 customers is we have 4 categories of customers. The top, whatever large enterprise account, right? Those are the top 100 accounts. Then the next group is what we call the strategic account. There's about 200 of those companies. These enterprise and strategic we sell direct, and then the others are called momentum accounts, and these are large scale things. Those we go through to our distributors and channels, right? So we absolutely sell to small medium enterprises, but we don't sell it directly. We sell it through our channel partners like CAPM and so on. And now, in terms of who buys these things, there's sort of 2 people who buy it. One is the asset OEMs themselves. So think about the pump manufacturer, right? So they will be interested in building much better digital twins of their pump, because then once they do it, they will be able to sell that digital twin of the pump. So they sell the hardware and the software of the pump to whoever is the end user, right? So we are selling to that asset OEM. The other one is the end user, meaning in a factory or in an oil and gas oil well, right? This Chevron or Total, right? They are buying all kinds of assets from various people. and they are interested in the digital twin of that oil refinery.
Right.
So we sell to the end user and we sell to the asset OEM.
Right.
Hey, Hans, I am getting an urgent thing. I will have to drop off. I'm so sorry.
Okay. No, I
have to take care of.
All right. All right,
Okay.
guys.
Okay, sure. Okay,
Thank you
bye-bye.
for-